Welcome to the deep dive. Today we are looking up, way up, at these incredible cosmic clouds,
Yeah.
nebulae.
Right. Beautiful, aren't they?
Absolutely stunning, but they're more than just pretty pictures. Yeah, I mean, you hear terms like stellar nurseries.
Exactly. Or even ghosts of dying stars. They
Yeah.
really are central to the whole story of the
Okay,
universe.
so not just eye candy.
Not at all. They're incredibly dynamic. Engines of, well, creation and destruction. Understanding them is fundamental to understanding, how everything formed, including us.
Right, that cosmic connection.
We'll definitely get to that.
So the plan today is figure out what these different types of nebulae are, how they actually form, how we even see them across, mind-boggling
And
distances.
why they matter. Why you listening should care about these giant clouds of gas and dust.
Perfect. Let's dive in. Where do we start? With starbirth, maybe?
That makes sense. That brings us to what we call emission nebulae, or the more technical term is HIR regions.
HI regions.
Yeah.
Got it.
Think of them as these huge sort of low-density clouds, mostly hydrogen, but it's ionized hydrogen.
Ionized meaning it's charged up.
Yeah, basically. Extremely hot, young, massive stars, either right inside the nebula or nearby, are blasting out intense ultraviolet radiation. Really intense.
Okay.
And that UV radiation has enough energy to knock electrons off the hydrogen atoms. That's the ionization. And when those electrons eventually recombine or the atoms get excited, they emit light. Mostly that characteristic reddish glow from hydrogen.
Ah, so the stars inside make the whole cloud light up.
Exactly. They're the power source.
Add a good example.
Oh, yeah. The Prawn Nebula, GUM 56, is a great one. It's down in Scorpio.
Prawn Nebula? Okay.
It's massive, about 250 light years across, and it's lit up by these really hot blue-white stars. O-type stars, we call them, blue giants.
Blue giants, they sound impressive.
They are, but they burn through their fuel incredibly fast. They live short, spectacular lives, and then, boom, supernova.
Wow. So they don't stick around long.
Not in cosmic terms now. A few million years, maybe.
And closer to home, is there one nearby?
Absolutely. The most famous is probably the Orion Nebula, M42.
Right. I've definitely heard of that one. You can see it, right?
Yeah, on a clear, dark night, you can spot it with just your eyes. It's only about 1,300 light years away, which is practically next door in galactic terms.
And it's big.
About 25 light years across. It's the closest region of massive star formation to Earth. Really a spectacular sight through a telescope.
And Hubble. Hubble looked at Orion, didn't it? Found something interesting.
Oh, yeah. Hubble revealed over 150 of these things called proplyds.
Proplyds, what are they?
They're protoplanetary disks, basically baby solar systems in the making. Young stars still wrapped in their cocoons of gas and dust.
Seriously. So we're seeing planets forming.
Potentially, yes.
Yeah.
It strongly suggests that planet formation isn't some rare event. It might actually be, pretty common out there.
That's incredible. And I heard something about bullets.
Huh, yeah. Supersonic bullets of gas. They're these high-speed clumps of gas literally shooting through the nebula, leaving these visible trails behind them. It's a really dynamic environment.
Okay, so emission nebulae glow because of hot stars inside. What's next?
Next up, let's talk about reflection nebulae. These are kind of different.
How so?
Well, they don't emit their own light. Instead, as the name suggests, they reflect the light from nearby stars.
Just like a mirror?
Sort of, but it's more like scattering. They're mostly made of tiny dust particles. And this dust is much better at scattering blue light than red light.
Ah, like why our sky is blue.
Exactly the same principle. So reflection nebulae often have this characteristic beautiful blue color.
Okay, cool. Example.
The classic example is the nebulosity around the Pleiades cluster, M45, the Seven Sisters.
Oh, right, in Taurus. You can see that cluster easily.
Yeah, it's very distinct, but 444 light years away. And if you look closely, especially in photos, you see this hazy blue light around the main stars.
So that haze is the reflection nebula.
That's it.
Yeah.
It was actually first noted, particularly around the star Merope, by Ernst Temple back in 1859.
And is that dust like left over from the stars forming?
You'd think so, but interestingly, no. The Pleiades cluster is actually just sort of drifting through a pre-existing interstellar dust cloud by chance.
Wow, like a ship sailing through fog.
That's a good analogy, yeah. And the starlight is illuminating the fog as it passes through.
And I read something about the starlight pushing the dust.
Yeah, that's right, radiation pressure. The light from bright stars like Merope actually exerts a tiny push on the dust particles.
A push from light.
Sounds weird, but yes. It acts like a sort of cosmic sieve, pushing the smaller, lighter dust particles away faster than the heavier ones. It's actively sculpting the cloud.
Wild. Okay, emission, reflection. What about the dark ones?
Right, dark nebulae. These are the opposite in a way. They don't glow, they don't
Yeah.
reflect much, they just block the light.
Block it.
Yeah, they're dense clouds of gas and dust, so dense and opaque that they obscure whatever is behind them, background stars, or even brighter nebulae. So they appear as these dark patches or silhouettes against the starry background. Cosmic shadows, really.
Like the Horsehead Nebula. That's a famous one.
Exactly. The Horsehead is probably the most iconic dark nebula. And there's also the Coalsack Nebula in the southern hemisphere, which is huge.
What are they made of? Still hydrogen?
Mostly hydrogen, yes.
Yeah.
But here it's primarily in its molecular form, H2, not ionized. These clans are really cold.
How cold?
Extremely cold, like 7 to 15 Kelvin, just a few degrees above absolute zero. Yeah. And the biggest ones, we call them giant molecular clouds, are enormous. They can be over 1 million times the mass of the sun, maybe 150 light years across.
And stars form in these too, right? You just can't see them easily.
Precisely. These cold, dark clouds are actually the primary sites of star formation. The density allows gravity to take over. But all that dust hides the process from view in visible light. You need infrared or radio telescopes to peer inside.
Okay, so birthplaces, reflectors, shadows. What about the end of a star's life? Do they make nebulae?
They certainly do. And that brings us to planetary nebulae.
Planetary.
Ah,
But they have nothing to do with planets, right? That name is weird.
totally misleading. Yeah, it's a historical accident. When astronomers first saw them with early telescopes, they looked small, round, and greenish, sort of like Uranus or Neptune. So planetary nebula stuck.
Huh. Who first saw one?
Charles Messier actually cataloged the first one discovered, the Dumbbell Nebula M27, back in 1764, though he didn't know what it was, of course.
So what are they really?
They are the final, beautiful farewell of stars like our sun, intermediate mass stars.
Not the really massive ones.
No, those go supernova. Stars roughly like the sun, up to maybe 8 times its mass. They don't explode violently. Instead, as they run out of fuel in their core, they sort of puff off their outer layers into space.
Puff them off, like smoke rings.
Kind of. These ejected outer layers form an expanding shell of gas. And then the star's remaining core, which is now exposed, gets incredibly hot.
Hotter than before.
Oh yeah, like 100,000 Kelvin hot. Hot enough to pour out huge amounts of ultraviolet light.
Ah, and that UV light.
Lights up the ejected gas shell. Just like in an emission nebula, it makes the shell glow brightly.
So it's the star's dying breath lighting up its own shed skin?
That's a pretty good way to put it.
Yeah.
They don't last forever, though. Maybe 10,000 years or so before the gas disperses too much and the central star cools down.
Are there famous examples people might know?
Definitely. The Ring Nebula M57 is a classic, looks just like a cosmic smoke ring.
Yeah.
And then there's the absolute stunning Butterfly Nebula, NGC 6302.
Butterfly? Does it look like one?
It really does, with these incredible wing-like structures. And the central star is one of the hottest known in our galaxy, a scorching 220,000 Kelvin.
Whoa. How did it get that shape?
Well, with the Butterfly Nebula, we think there's a dense, donut-shaped ring, a torus of dust and gas around the central star.
A donut?
Yeah, made of stuff like silicate crystals and dust grains. This torus seems to block the outflow in the middle and channel it outwards, creating those bipolar wings.
So the torus shapes the nebula.
It seems so. And it's fascinating because planetary nebulae come in this incredible variety of shapes, spheres, rings, butterflies, hourglasses. It's not fully understood why. Maybe companion stars or magnetic fields played a role too.
Okay, so that's the end for sun-like stars. What about the big ones? The ones that do explode?
Ah, yes. The grand finale. That leads us to supernova remnants.
Remnants.
Leftovers. Exactly. These are the expanding, chaotic clouds of debris left over after a massive star explodes in a supernova. One of the most energetic events in the cosmos.
Must be quite a mess.
A beautiful, important mess. The Crab Nebula, M1, is the textbook example.
M1, Messier's first object, right?
That's the one. And it's amazing because we actually saw the supernova that created it. Chinese astronomers recorded it in 1054 AD as a guest star visible during the day.
Wow. And we can see the cloud expanding.
We can. By comparing old photos from, say, the early 20th century with modern images from Hubble, you can literally measure the expansion of the gas cloud over decades. It's like watching cosmic history unfold.
So what's the significance of these remnants, besides looking cool?
They are hugely significant.
Yeah.
Supernovae are where most of the heavy elements in the universe get created and
So
distributed,
heavy elements like...
like oxygen, carbon, iron, silicon.
Yeah.
all the stuff heavier than hydrogen and helium. These elements are forged inside massive stars during their lives, and then even more are created and scattered violently across space during the supernova explosion itself.
Scattered into the interstellar medium, the space between stars.
Exactly, they enrich that medium. And that enriched material then becomes part of the next generation of stars and planets. It's cosmic recycling. Oh, and fun fact, recent studies of the Crab Nebula's pulsar, the spinning neutron star left at its core, are helping explain weird things like the nebula's zebra pattern. Still lots to learn.
Okay, so we've seen birth clouds, reflecting clouds, dark clouds, dying sun clouds, and exploding star clouds. That covers a lot.
Yeah.
What's the big takeaway here, the bigger picture?
The big picture is that concept we just touched on, cosmic recycling. Nebulae aren't isolated phenomena. They are fundamental parts of this ongoing cycle in the universe.
A cycle of birth, death, and rebirth.
Pretty much, yeah. Old stars die, scattering enriched material through planetary nebulae and supernova remnants. This material mixes with the existing interstellar gas and dust, forming new nebulae.
Which then collapse to form new stars and planets.
Exactly. Providing the raw materials, the hydrogen and helium from the Big Bang, plus all those heavier elements from previous stars for the next generation. Our own solar system formed from such a cloud.
And this is where it connects back to us, right? The whole we are stardust thing.
Absolutely. This is not just poetry, it's literal fact. Think about it. Every single atom of oxygen you're breathing right now,
Yeah.
the carbon in your muscles, the calcium in your bones, the iron in your blood, none of that was made in the Big Bang. It was all forged inside stars generations ago.
Forged inside stars.
And then ejected into space through stellar winds or supernova explosions, becoming part of these interstellar clouds, these nebulae, which eventually formed our sun and Earth.
Wow. So we really are made of star stuff.
We really are. It's a concept that, has a long history. People suspected it, but it was really confirmed scientifically back in the 1800s with spectroscopy.
Spectroscopy. That's breaking down light.
Right. Scientists like Kirchhoff and Bunsen figured out how to read the chemical fingerprints in starlight, proving the stars contain the same elements found on Earth. Carl Sagan, of course, did a wonderful job popularizing the idea later on.
It's a pretty profound thought. Changes how you look at things.
Definitely.
So how did we even get to the point where we can see these nebulae in such detail? You mentioned Messier trying not to mistake them for comets.
Right. Early observations were limited. Messier's catalog in the 18th century was crucial for just mapping out these fuzzy patches. But the real game changer has been modern telescopes.
Like Hubble.
Hubble, absolutely. The Hubble Space Telescope gave us those incredibly sharp, iconic, visible light images. Think of the pillars of creation in the Eagle Nebula, that's Hubble. It revolutionized our view.
And now we have the James Webb Space Telescope, JWST. How is that different?
JWST is another leap forward, mainly because it sees primarily in infrared light.
Infrared heat radiation.
Essentially, yeah. And the key thing is, infrared light can penetrate through the dense clouds of dust that block visible light.
Ah, so it can see inside those dark nebulae and dusty regions where stars are born.
Precisely. It's like giving us infrared X-ray vision for the cosmos. We're seeing star-forming regions in places like the Carina Nebula with unprecedented clarity. And it's also amazing for studying the composition of things like that dusty torus in the Butterfly Nebula we talked about.
So Hubble sees in visible light mostly, and Webb sees in infrared. Why does Webb need to be so cold?
Good question. Because Webb is looking for faint infrared signals from distant objects, the telescope itself can't be warm. If it were, its own heat would just swamp the detectors with infrared noise.
So it has to be freezing cold to see clearly.
Extremely cold. Around minus 153 Celsius or minus 244 Fahrenheit. That allows it to pick up those faint signals from the early universe and deep within nebulae.
Incredible technology. Okay, before we wrap up, maybe hit us with some really cool, mind-blowing nebula facts.
Okay, yeah, let's do some fun facts. Get this. The Eagle Nebula, M16, it really does look like an eagle landing. And those famous pillars of creation are sort of tucked under its wing in the images.
Nice. What else?
There's one called the Giant Squid Nebula. It stretches about 50 light years long. It looks like, well, a giant squid formed by gas flowing from a star.
A 50-light-year squid.
Amazing. And then there's the Manatee Nebula. What's cool about this one is you basically can't see it in visible light. It only really shows up when you look with radio telescopes.
So some nebulae are invisible unless you use different kinds of eyes.
Exactly. Shows how much we might be missing. And thinking about size, while star-forming clouds can be huge, like thousands of light years.
Yeah.
Some nebulous gas clouds around entire galaxies, like one called NGC 262, can stretch between 300,000 and maybe 1.2 million light years across.
A million light years of gas.
Mind-boggling scale. And one more. The Tarantula Nebula. It's not in our galaxy. It's the Large Magellanic Cloud, a neighbor galaxy.
Okay.
It's such a huge and active star-forming region that if it were as close to us as the Orion Nebula, it would cover an area of the sky half the size of the full moon. No, wait. Much bigger than that. It would take up half the entire sky.
Half the sky. Just one nebula.
Imagine looking up at that. And remember the Butterfly Nebula's central star? 220,000 Kelvin. Just ridiculously hot.
Those are definitely some great facts to chew on.
So yeah, wrapping it all up, nebulae really aren't just pretty space pictures. They're fundamental. They are the cosmic architects, constantly building, shaping, reshaping the universe.
From star birth, planet formation,
To the recycling of elements, the very elements you're made of. It's all connected.
you are literally connected to these vast, distant clouds. Our existence is tied into this grand cosmic story playing out in nebulae.
Absolutely. And the story's not over. With tools like Webb giving us these incredible new infrared views, peering deeper than ever before, well, it makes you wonder.
What secrets are still hidden in those clouds?
Exactly. What more will we learn about how the universe works, where we came from, and maybe even where it's all going? What mysteries do these celestial canvases still hold?